So today, BC students, we end off with our last lesson of the infamous Chapter 4 with 4-6. Now, these are more integration by parts, so we're going to be using the LATE acronym from last time. However, these are the slightly harder integration by parts, okay? The hardest ones you won't see until Calc 2 in college. We won't do those yet. We might do them in the calculus club, though. So, here we go. You've got the integration of x squared e to the 4x. Right away, you see a variable times a variable, which in derivative world would be a product rule. In integration world, it's integration by parts, of course. So, LATE, x squared, algebraic. E to the 4x, exponential. The higher one gets the u. The lower one gets the dv. And technically, with the dv, you're supposed to also put the dx. Now, of course, you'll still get it right if you don't. In college, they can't offer everything. Okay, so if u is going to be x squared, then du is going to be the derivative of u, 2x to the first, with a little dx on the side. If dv equals e to the 4x, then wouldn't v be the integration of dv? So the integration of e to the 4x, exponential functions, remember, stays the same, divided by two things. The natural log of e, which is just 1, and divided by the chain rule of 4x, which is 4. All right? There's your setup. And now we go to our famous formula. The integration of a variable times a variable is performed by uv minus integral v du. Pretty easy, right? So, what's uv? Okay, u is x squared times v, which is e to the 4x over 4. All right, this has already been integrated for us. Minus the integration of v, e to the 4x over 4, times du, which is 2x dx. All right, and I do see right away I could reduce 2 over 4, cross-cancel those. Could we just make that a 1/2 and even better shove it outside the integral, right? Okay, so now let me clean this up a little bit. What is this? This is x and then e to the 4x, right? X e to the 4x. So let me just, because I made a mess in there, so let me just put that. Okay, this is what we're trying to integrate right here. Okay. So remember, you just do uv minus integral v du, you do your integration by parts, you get down here, and then this has already been integrated, so you just have to integrate this and you're done, right? Okay, so let's integrate, x times e to the 4x. It's a variable times a variable. It's another parts. It's a parts within a parts, often referred to as double parts. So it's double integration by parts. Okay, well, let's see. What can we do? Well, I want to note something here. Do you notice that this is actually better? We went from x squared times e to the 4x down to x times e to the 4x. See how the x squared got reduced down to x to the first? I bet if we do one more integration by parts, x will go down to some kind of constant. You see how it's kind of taken a derivative in there, right? So second degree x, first degree x, 0 degree x. So I'm guessing the next stage is going to be a 0 degree x, which is a constant, e to the 4x. And that we could integrate, okay? So just note to self off to the side, okay, if you want to put that in your notes. So parts is actually reducing the strength all the way down to something so weak we can easily integrate a constant that we can move out, and an e to the 4x. Matter of fact, we just integrated e to the 4x. We can do that. All right, I've cleaned it up a little bit, but the thing I want you to do is put a box around the integral of x e to the 4x, because we must integrate that by another parts, and then we're going to insert what we get back into the box. If you don't put a box in your notes, you're going to lose track of it. Students do it all the time, and you're going to forget something else we're about to talk about with the negative 1/2. So, box it up. So over here on another board, we'll focus on how to integrate x e to the 4x. Okay, so LATE again, late. X is algebraic, of course, and e to the 4x is exponential, of course. The higher one is u, the lower one is dv. See, you really get used to this stuff, okay? Now, if u is x, I can also find du, which is the derivative of x, which is 1 dx, or just dx. If dv is e to the 4x, then v is its integration, and the integration of e to the 4x is itself divided by natural log of e, which is 1 again, and chain rule of 4x, which is 4. If you don't do u substitution, you have to divide by the chain. If you do u substitution, which would not have been necessary here, it's too simple, then you don't divide by the chain because the du and u process does it automatically. So right here, if you integrate without u substitution, always divide by the chain rule. That's the deal. Okay, so this integral equals uv, so u is x, and v is e to the 4x over 4. There's my uv, minus the integral of v times du. Okay, that's v du right there. So uv minus integral v du. Then you ask yourself, is this another parts or can I do it? Oh no, we can do this one. See that 1/4 right there, coefficient? Move that out. And we'll just take it out of there. Oh yeah, now we're just integrating e to the 4x, which we literally just did here anyway. That should be very easy. So wasn't that what I promised? Right? Didn't we start off with x squared e, and then we got down to x times e to the something, and now we got down to constant times e to the something. So if you keep pursuing, eventually things will work out in many of these parts questions, all right? Until we do the next problem. Okay, so let's see what I should do here. Shouldn't that just be 1/4 out in the front, right? Isn't that better? X e to the 4x, no parentheses necessary, right? Okay, 1/4 carries. The integration of e to the x, or e to the 4x is e to the 4x over 4 yet again, right? Don't even put the plus c yet, okay? Like here we integrated to get from dv to v. We didn't put a plus c. Here we just integrated, we didn't put a plus c. Wait till the very end and just put one general plus c on everything. Okay, isn't this as far as we can take the integration? Well, I guess you could do this. You could make this 1/16. See the 4 times 4 right there? So if you want to do that, let's just make that 1/16 e to the 4x and a minus, and I'll just take this circle and cross it out, okay? So the integration of e to the 4x times that x is all of this right here. Now, all of that will replace this, which was in the box. So all this must go into the box right here. Now I'm going to continue over here. So let's see, we've got, let me take this 4 out and make it 1/4 x squared. E to the 4x, okay, minus 1/2 times the box. The box gets replaced by parentheses. When you replace things in math, you put them in parentheses, okay? All that stuff over there is going to go down here. 1/4 x e to the 4x minus 1/16 e to the 4x. So hopefully all of you who are, if you're good enough to be in BC, then you're good enough to look at that and say, okay, it's a little tedious, but I can get there. I know just to do parts twice. And honestly, after teaching for 30-something years, that's really what separates honor students and AP students from the rest of the pack. Okay? The best of the best students in America and all over the world, what separates you is I see how to do it. I don't care how long it takes. I know how to do it, and I'm willing to put in the work to get to the answer. All right? That's what makes you calculus students. You're willing to put in the work and get down to the answer instead of going, oh no, it's more than 3 steps. Okay? I have some students in my classes, they complain when the problem goes past 2 steps. I'm like, seriously? So you get down here, and here's what students forget. So number 1, if you don't put the box, you look back through your work and you're like, ah, crud, where did that thing go? And you lose track of it, okay? And it wastes time. I went right to the box because I had my eye on it, okay? Number 2, the other thing students forget. See this negative 1/2 right here? They forget to distribute the negative 1/2 into this thing we got over here that's now sitting in here. They don't realize, oh wait, I just put this back over here. I forgot the negative 1/2 goes to both of those. A basic middle school property. And of course, there's a lot going on, so it's easy to overlook that. So remember to distribute whatever's in front with the minus. So now you're going to get 1/4 x squared e to the 4x. Okay, minus times a positive, so that's a minus. 1/2 times 1/4 is 1/8 x e to the 4x. And then negative 1/2 times negative 1/16 is plus 1 over 32 e to the 4x. And then finally, throw on a plus c at the very, very end. And you have just done your first double parts question right there. And it's very nice how the fractions kind of get like smaller and smaller, and the x squared goes to an x, goes to a constant, how it kind of descends. It's a very nice problem there, okay? That's how you do double parts. All right, let's check out the next example. What happens when double parts doesn't work? Watch this. So letter B, we've got e to the x times sine of x. I love this problem, all right? Calculus teachers, calculus students, they really enjoy this problem once they get to the end, and it's like, that was so cool. All right, so here we go. So first of all, I read out the acronym LATE, and after I write that out, I say, e to the x, you're an exponential. Sine of x, you're trig. So the higher one is sine, that's u. The lower one is e to the x, that's dv. And as long as you kind of follow that system, things should work out a lot better than if you went the other way, by the way, and tried to let u be e to the x and the other one be dv. No, no, no. Okay, so if u is sine of x, then du, the derivative of sine, is cosine of x times the chain rule of 1. And also, I'm going to put a dx with the dv and a dx over here with the du. All the d's go together. And then the integration to get v. The integration of e to the x is itself e to the x over natural log of e, which is 1, and over the chain rule of x, which is also 1. The integration of e to the x is indeed e to the x. Okay? So, now we go to the formula. uv, sine of x is u. V is e to the x. uv minus the integral of v du. E to the x cosine x dx. All you have to do is integrate this and you're done. So the integration of this, variable times variable, it's another parts. Maybe it's double parts. All right. Well, box it up, first of all. Otherwise, you're going to go astray. Put a box around it. Students will forget to distribute the negative to whatever we get later. Don't forget that. And also, they'll lose the box. They'll lose where they left off. I'm even going to draw a line. Here, we'll just draw a line right here. Okay, part two. Part two. How do you integrate e to the x cosine of x? Another parts. All right, late. And e to the x, you're at the bottom. Cosine of x, you're second from the bottom, but that's enough to be called, here, I'll just use that darn slash that's in my board over here as an equal sign. U equals cosine of x. dv equals e to the x, technically dx. So that covers everything else. Okay, and remember, parts, don't we cover like half the problem with u, half the problem with dv, roughly? We got half and half. Jigsaw puzzle fits together. U equals cosine. What is the derivative of u? The derivative of cosine is negative sine of x times chain rule 1 with a dx on the side, okay? If dv equals e to the x dx, then v is the integration of e to the x. We just did that. It's e to the x. It's itself, right? Plus c, but remember, wait till the end. Okay, now we got something. So let's write this. What are we doing? We're doing the integration of this box right here. Integration of e to the x cosine x dx. The box, basically. If you want to put another box, the more boxes probably the better. Equals uv cosine x is u. V is e to the x. Minus the integral of v, e to the x, times du. Don't put minus sine of x. That's going to look like e to the x subtract sine of x. Don't do it. Put positive sine of x dx and take that negative and throw it up to the front of the e. Or even better, bring it all the way out and make it a plus sign, because it is going to be plus, right? Okay, so please mind your negatives, right? All right, now all you have to do is integrate e to the x sine of x dx, and we can stuff it back into the box and be done with this. All right, so the integration of e to the x sine of x. Oh my gosh, do you see what's happening here? It's another variable times a variable. Double parts didn't work. Maybe it's triple parts. Maybe it's 4 parts, 5 parts, I don't know, because it's not working so far, is it? We started with e to the x sine of x right here. Then we got to e to the x cosine of x, but it was minus technically, right? Then we got back to positive e to the x sine of x. And so we just keep ending up with an exponential times a trig function. We're in this endless loop. In fact, it is an endless loop. I'm going to write that down. Endless loop. This is not double parts. This is infinite parts. If you keep doing integration by parts, you will never escape an exponential times a trig function. Now this is important to notice though. We did go from, let's ignore the e to the x, because isn't the e to the x just there every single time? So let's ignore the thing that stays the same. Notice the thing that's changing. Positive sine, this was a negative cosine, so to speak, right? Now it's a positive sine again. Seems to be kind of oscillating back and forth, right? Alternating, all right? Now I want you to notice that this right here, the thing we have here, is the exact same as the original function. Everybody see that? They are the same thing. When you get that in a parts problem, there is hope. So what's the hope? What's the breakthrough here? Okay, if you ever do parts and then you do parts again, if you get the same thing as the original question, I want you to write out everything you have so far so I can show you a little trick here, okay? Matter of fact, let's go over here and try it on a clean board. All right, so write the original question first. I integrated e to the x sine of x dx, right? What did I get? I got sine of x times e to the x minus box, here's my box, integration of e to the x cosine of x dx. Okay, remember this was in a box. This is exactly what we had right here. All right, now let's replace the box with what? All this. Wasn't the box all this by another parts? Okay, so go back over here. You can see why it's important to box up your work. So let me write sine of x e to the x minus parentheses cosine x e to the x, I'm going to need a lot more parentheses than that, plus integral of e to the x sine of x dx parentheses. So I just replaced the box with what I got over there. Let's drop down this original problem. So apparently the integration of e to the x sine of x is equivalent to sine of x times e to the x minus another parts. Now, let me show you something really cool. Wouldn't this subtraction sign actually distribute through here? Isn't that the thing I mentioned earlier that people forget? Let's distribute that through there, okay? So you're telling me the integration of e to the x sine of x dx is equal to, let's move this e to the x up to the front. It looks better that way. E to the x sine of x looks normal. Minus, let's put e to the x in front of cosine x. Minus times a positive is a minus integral of e to the x sine of x dx. And wasn't that the thing we noticed was the same as the original problem? All right, so here's the original. Here it kind of pops up again, but in a negative fashion. I need to try to solve this. I need to solve for the integration of e to the x sine of x dx. If anybody's thinking this at home, you are super duper clever. If you could add this expression to the other side. Hey, we've added x to both sides. In middle school, you subtracted 2 from both sides, added 37 on both sides. I don't think you've ever in your lifetime added an integral to both sides, but guess what? It follows the rules of math. I'm going to add the integral of e to the x sine of x dx to both sides. It will cancel here, and one of them plus one of them makes 2 of them over here. 2 times the original problem equals e to the x sine of x minus e to the x cosine of x that's left over here. Okay? Are you kidding me? You mean if I want to solve this and get a final answer, all I have to do is divide both sides by 2, and I've got the original integrand isolated. Wow. Now that's clever. That's why it was a good sign that we got the same integral over there as the original function, because you'll end up adding it over to itself. Sometimes you'll add one of them, 1 plus 1 is 2. Sometimes this will have a 7 in front of it, and you'll add it over and get 7 plus 1 is 8. But whatever it is, it's not always going to be 2, but it will be a constant. Divide everything by 2, or even better, multiply by 1/2 is better in math. I'm going to cross this 2 out. I'm going to divide over here by 2 or multiply by 1/2. And that is your final answer. And finally, I put a plus C on it. How about that for a clever, clever problem? Okay? We'll go over this in class as well to make sure you understand. Now, the last thing we'll discuss in chapter 4 will be absolute values, because those functions are kind of a little funky, so you have to be able to take the derivative and integrate absolute values. Now, the absolute value bars were first proposed by number 8 ranked Weierstrass, a German mathematician, obviously with a name like Weierstrass, right? Weierstrass was the last mathematician who made it into the top 10 all-time mathematicians. The only one in the 1800s who made it in. He discovered the concept of absolute values in 1841 and proposed the bar, and we've used it ever since, and it's very, very, very useful. Okay, so 1841, very recent discovery in this class, actually. Now, graph f of x. Okay, how do we graph y equals just x squared minus 4? Let's just start with that. Well, of course, everyone in my class should know that that's a parabola shifted down 4. All right, so let's do a parabola shifted down 4 from the origin. And don't make this a solid line, actually. Make this a dashed line at first, because this is not the full story here. Okay, so there's my parabola shifted down 4, but wait, doesn't it have bars on it? So what do bars do to things in math? Okay, well, bars keep things that are positive, positive. But they make things that are negative into positive. So you see all this stuff above the x-axis that's above sea level? All the positive stuff does not change. The absolute value of a positive is still positive. I'm going to fill this into like right there. Also, the absolute value of 0 is 0. So if it's on the x-axis at sea level, the absolute value of 0 does also stay the same. So that's not going to change. I'm going to fill in this right here as best I can. And you have like 2 pieces. Now here's the question, the middle piece. See this middle piece right here? It's all below sea level. It's all negative. But when the bars are placed on this, it makes negatives into positives. It actually takes this little U shape and it folds it up above the x-axis like that. Now it's hitting positive 4 instead of negative 4. Now don't erase this on your paper because you've drawn it, but I can take off the dashed lines if you want to kind of see what this looks like. You should just go ahead and leave it on your paper, and this doesn't even matter anymore, right? So there you go. So it's this weird parabola that's been folded over, and all of its negatives become positive, okay? So that's how you handle absolute values. Now, to answer several of these questions, really the only practical way to do it is to know that picture. If you don't know that picture, you're going to have a really tough time answering some of these. Okay? So, graph done. Now, write a piecewise function for this parabola-ish thing. And to do this, maybe we should do like an F test here, just to show you what's happening, all right? So let's talk about the absolute value of x squared minus 4. First of all, where is it neutral? What could you plug in for x to get a 0 on the inside? Well, 2 squared is 4 minus 4 is 0. So 2 is going to produce a neutral. Also, negative 2 squared is 4 minus 4 is 0. All right? So those are your two neutrals. Guess where these points are right here? Negative 2 and positive 2. They're the x-intercepts. I said they were where they were neutral, right? Now, okay, what is the absolute value of x squared minus 4 if you pick a number larger than 2, let's say? Okay, if you pick like a 100, all right? And you plug that in. 100 squared minus 4 is positive. So the absolute value stays the same. Now for once, I don't want you to put plus here. I know that they're plus, plus, plus because the absolute value is always positive, okay? We're not going to put that. If you plug in a number larger than 2 and you get a positive on the inside, the absolute value of it stays the same. I want you to put x squared minus 4. This is going to be more important today, all right? It stays itself. Plug in like negative 100. Okay? Yeah, it's positive, but I want to know more information today. Negative 100 squared is positive, large number, minus 4 is positive. So the absolute value of x squared minus 4 does not change. It's x squared minus 4, whatever that works out to be for that number. But if you pick a number between negative 2 and 2, like 0, and you plug that in, you get 0 squared is 0 minus 4 is negative. Now, yes, the bars make it positive, but that's not the point today. The point today is that you understand what functions are actually happening here. 0 minus 4 is negative. What's the absolute value of a negative, or what does it do? Don't tell me positive. What do the bars do when the inside is negative? Doesn't it switch the sign? So it's more about, does it switch the sign or not? It's less about, is it positive? I know it's always positive, okay? It switches the sign when the inside is negative. So the absolute value of x squared minus 4 in this region right here will change the signs, check this out, to negative x squared and plus 4, okay? So for instance, let's take like x equals 1. What is the absolute value of 1 squared minus 4? 1 minus 4 is negative 3. The absolute value of negative 3 is positive 3. Or you could use my new formula. When the interior is negative like this is, you can just convert to the formula negative x squared plus 4 and drop the bars. See, we're trying to find a way to drop the bars here. So now let's retest it. X equals 1 into my new formula. Negative 1 squared plus 4. 1 squared is 1. Negative 1 plus 4 is positive 3. It checks out. So the new thing I'll need my BC and eventually AB students to know is that when the interior of an absolute value is positive, you leave it alone. You leave it the same. But when the interior produces negative numbers, like in here, it changes every sign to opposite to be valid, okay? So here's your piecewise function. F of x equals curly brackets. Enough, we're going to stack 3 functions in here, by the way. All right, first of all, we have x squared minus 4. It stays the same. When? When it's below negative 2. X less than negative 2. And then here, between negative 2 and positive 2, it switches. Negative x squared plus 4 for negative 2 less than x less than 2. Now somebody needs to get the underline here. It really doesn't matter because at negative 2 and positive 2 it's neutral. So with 0, 0 works in either formula. Technically, usually you put the underline with the one that's positive, the positive case, not the negative case. but it wouldn't matter if you put the underlines here and not there. Just pick one or the other, okay? And then finally, it goes back to being itself unchanged when x is greater than or equal to 2, if you want to put the underline there, okay? That's your piecewise function that models this picture up here. Piece 1 is there, piece 2 is the hump, and piece 3 is there. 3 pieces, 3 equations. Now find f prime of x, do the derivative of this. Okay, this is what I need to talk about with you. You can't do the derivative of an absolute value as just one function. You have to do it as a piecewise function. So here's the problem. With those bars on there, all right, you can't do the derivative of an absolute value. You can't integrate an absolute value. That's like 2 of the big 3 in calculus. You've got to change it into something without the bars to even be able to handle it. That's the theme of this last section right here, okay, the last page. So, what's the derivative of f of x? Well, you couldn't have done it with the bars. You can only do it as a piecewise function. X squared minus 4 goes to 2x. Negative x squared plus 4 goes to negative 2x. And x squared minus 4 goes to 2x. So the top one was what? X less than or equal to negative 2. The middle one was negative 2 less than x less than 2. And the last one was x greater than or equal to 2. So this is how to visualize an absolute value as a piecewise function. Okay? I'm going to show you another way that's probably faster, but it is pertinent and imperative that you know this method as well right here. Now find f prime of 1. Isn't that the slope of the graph at 1? Let's see, where's 1? That's in here. Aha. The slope is negative. The graph is decreasing, so I should get a negative. Now, I take 1. I go to my piecewise function, don't I? Go to the piecewise function, and 1 is between these two numbers, so I have to plug it into this formula. Negative 2 times 1 is indeed a negative number, like I promised. It's negative 2, all right? Now, I'll probably show you a shortcut on the sample test. There's a short way to do that as well. Heck, I'll show it to you here. Okay, now, if you don't want to go through the whole piecewise, which you'll need to understand that later, but if you don't want to go through that entire phase there of doing all this, here's what else you can do. Test 1 in the original function quickly and say, okay, 1 squared minus 4 is negative 3. The inside is negative. So to take the absolute value of a negative, I convert it to this version, opposite signs. Then take the derivative of this, and that'll give you the negative 2x. And then plug in 1. Okay? We'll go over more of that later, but that is a shortcut, a major shortcut. Now, f prime of 2. Okay, this is a problem. 2 is right on the phase change. One of the 2 phase changes. You've got a 2 and also a negative 2 phase change. So when we say f prime of 2, then you have to plug it into not just this one, but also this one, because this one is at 2 and this one is virtually like super duper close to 2, close enough. They have to agree like we did on that earlier test. If you plug 2 into here, you get 4, right? 2 comma 4, or that's the slope. If you plug in 2 to this formula, you get negative 4. Mismatch. What is a mismatch in the derivative? A mismatch in the original function is a jump, right? Original function mismatch is a jump. But what is a mismatch in the first derivative? Isn't that what we call the crooked fit? Do you remember this? Crooked fit. There must be a crooked point at 2. Wait a minute. Look at the graph. Everybody see that crooked point there? That's a sharp corner. You can't take the derivative at a sharp corner. No wonder it's a mismatch. So you could do it by the piecewise function and figure out it's a mismatch. What's the shortcut? Know the graph I showed you earlier. The derivative at a sharp corner does not exist because you can't take the derivative at what we call a cusp, sharp point, okay? So way faster to draw that than it is to do all the piecewise stuff. But you do have to understand the piecewise stuff for what we do next. And finally, we have letter H, where we integrate from 0 to 3 f of x dx. Now, what is f of x? It is the absolute value of x squared minus 4. Okay, now wait a minute. I just told you that you can't take the derivative of an absolute value. You've got to get it out of its bars. I also just told you earlier that you can't integrate absolute values. You have to get it out of your bars, right? You can't do anything with the absolute value, all right? Do you understand the words that are coming out of my mouth? You can't integrate or differentiate or do anything with the absolute value. All right, so what do? Okay, where was the shape changing? Where was its phase change? Remember the picture? Wasn't it at 2 where the sharp corner happened? You can't integrate from 0 to 3. Integration, by the way, is area under the curve, the area of the space, which we're getting to in a later chapter. You know what you can do? You can integrate from 0 to 2, where the sharp corner happens. Plus, you can add the rest of the area, which you're not supposed to know yet, from 2 to 3. So you have to split it up around the phase change. Now, what are we integrating? Can you just drop the bars? Hold on there a second. Okay? If the inside of the bars is positive, drop the bars. If the inside is negative, drop the bars and change all the signs, right? So, let's pick any number between 0 and 2. Like 1. If you test out 1, you get a negative inside the bars. 1 minus 4 is negative. So the absolute value of a negative means change to negative x squared and plus 4. Okay? Now, pick a number between 2 and 3. Don't pick 2 because it's neutral. That won't tell you anything. But you can pick 3 actually because it's not neutral. You can pick 2.5, 3, 2.1. Just don't pick 2. All right? Most people go with 2.5. 2.5 squared minus 4 is more than 4 minus 4, which is positive. I think 3 squared minus 4 is easier. It's positive. If it's a positive inside, you drop the bars, you keep it the same. So it's really a choice of, do you keep it the same or do you change everything? All right? Negative territory, change everything. Positive territory, change nothing. That's it. Now, the only way to integrate an absolute value is to split it into 2 functions and then integrate it. So I really just wanted to end off this chapter with just how do you transform these weird square roots, and then you're good. So to end off chapter 4, we will integrate this, which is negative x to the third over the new power 3. Integration of 4 is 4x, because the derivative of 4x is 4. From 0 to 2. Plus x squared goes to x cubed over 3. Minus 4 goes to minus 4x. Evaluated from 2 to 3. All right. Now, this isn't hard, but there are fractions, there are negatives. Keep your head on straight here, okay? So plug in 2 first. 2 cubed is 8, then throw the negative on it. Negative 8 thirds. Plus 2 times 4 is 8. Okay, that's the top number. Minus bottom number. 0 cubed and 0 times 4, the whole thing's just 0. Plus sign carries down. Plug in the top number. 3 cubed is 27 over 3 is 9 minus 3 times 4 is 12 minus the bottom number. 2 cubed is 8 over 3 minus 4 times 2 is minus 8. So we need to make something nice out of this whole mess here, right? Now, I know you're trying to kick back to your old training from middle school and say, shouldn't I just get a common denominator between the 8 thirds and disguise 8 as a 24 thirds? I would not. And you're trying to make this minus 8 into minus 24 thirds and get common denominators inside the parentheses. See, you're going back to your training. Oh, how you're trying to remember your training. That was James Bond, Skyfall.
How you're trying to remember your training now.
I'm teaching you how to really think about math and not how to do what other people have taught you, okay? In many cases. So, turns out when you have a whole list of fractions and whole numbers, this is going to be better and far more efficient. You just drop the parentheses off the first one. Negative 8 thirds plus 8. Don't get a common denominator, okay? Minus 0, gone. 9 minus 12, okay, you can do that because they're like terms. These aren't like terms. They're not even like fractions. 9 minus 12 is negative 3, all right? See this negative? I'm not going to get a common denominator. I'm going to distribute the negative and get minus 8/3, and minus minus makes a plus 8. This is what I'm going to do instead. I'm going to gather all my integers. I like to gather my integers, okay? I'm going to gather all the integers together. I'm going to gather all the thirds together, because you can see there are a couple of thirds here. And it's basically like like terms. And then I'm only going to get one common denominator in the very end if I even need one. Sometimes you don't even need one. That's why you do this method, okay? So don't get over eager and start trying to make common denominators yet. Okay, here's what we'll do. And by the way, sometimes you get a negative 8/3 and a plus 8/3 and they completely cancel and you wasted your time with a common denominator. That happens sometimes. Okay, integers. 8 plus 8 is 16, minus 3 is 13. So I gathered my integers. Minus 8/3 minus 8 more thirds is minus 16/3. Okay? Sometimes that'll come up to be something like minus 30/3, which is negative 10, which means you didn't need a common denominator because you just got a whole number. That does happen, by the way. You'll see it. Okay, now when you get to the end, now get a common denominator. 13 can be disguised as 39/3 minus 16/3. 39 take away 16 is 23/3. There's your answer. All right, it's all about technique.
Hold it now.
We started with EX. EX? That's just baloney. U is X. U is X, dum-dum. E to the X. Did I just say E to the X? And the integration of it. 3 squared is 27, or 3 squared. So you keep it the same, dum-dum. I did it again.